All right, so in our second hour today, and that hour is going to be more like 35 minutes. But in our second time today, we're gonna focus on the second law of thermodynamics. And the second law of thermodynamics is kind of couching the idea of spontaneity and when spontaneity happens. So again, we just want to kind of reiterate our terms here, make sure that we're on the same page. So spontaneous processes will or will not occur under given conditions. And so what it means to be spontaneous is that it's happening without outside interference. So if we're describing a spontaneous process here at room temperature in Vincennes, Indiana, then we're going to describe a process that's going to occur at these conditions and is going to require some amount of energy. But ultimately, what we're looking for is this. Spontaneous processes have a positive entropy of the universe, meaning that if I'm looking at, remember, universe is system plus surroundings. So in order for a process to be spontaneous, we have to see a net increase in the amount of entropy overall. Whether that entropy input is happening to the system or is happening to the surroundings, that's not as important. What matters is that the entropy of the universe is increasing in a spontaneous process. So what does that mean? Well, we can't pinpoint necessarily a concrete set of conditions that is going to happen. Sometimes we need to have an input of energy to get something to be spontaneous. Sometimes we're going to have processes that are incredibly kinetically slow, yet still spontaneous. For a non-spontaneous process, however, what we're going to find is that that process will not, does not, cannot occur unless we change our conditions. Whether that's changing the temperature, changing the pressure, or just out and out changing the total environment of the system. Non-spontaneous processes have a negative entropy of the universe, meaning that the entropy of the entire universe, as far as this system is concerned, the entropy is having a net loss. So the second law of thermodynamics is one that states that all spontaneous processes lead to a change of the entropy of the universe in the positive. Now, some things to know about that entropy. First of all, entropy, enthalpy, all these thermodynamic quantities, completely independent of kinetics and speed. You can have a spontaneous process that is kinetically very slow. You're living through one right now. Radioactive decay of the carbon in your body, because you have small amounts of carbon-14 in you. That radioactive process is slow. The half-life of that is 5,700 years. But it is spontaneous. It happens without outside interference. It just happens really slow. We have done chemical reactions in lab that take hours to reach some kind of satisfying end. Think about the decoloration of the crystal violet dye. We observed it for 20 minutes. There was still color in that test tube, in that cuvette vial at the end of the 20 minutes. We did the esterification reaction. You boiled that sucker for an hour and a half. We aren't still 100% certain we hit equilibrium, even after an hour and a half. Some reactions are just kinetically slow. Some are incredibly kinetically fast. Has nothing to do with thermodynamics. But what we can see, again, using a reaction coordinate diagram here, is that this change in energy and the activation energy that gets it started, there is something to be said about this kind of reaction in terms of spontaneity. Now, it's not the only part of it, and we'll talk about that more tomorrow, but definitely there's going to be an energy component to this that is going to impact spontaneity in one direction or another. So what are some things that are favorable or disfavorable in terms of entropy? Well, for the things that are favorable, they are things that generally encourage the process to happen as written. And generally speaking, we're looking for processes where we either see the entropy of the system or the entropy of surroundings increasing. We know that by the second law of thermodynamics, that entropy has to increase in order for a process to be spontaneous. So we're looking for entropy increases, or we're looking for heat enthalpy decreases. Because if we go back to thermodynamics, if we go back to thermochemistry, we can think of a lot more reactions that are exothermic than ones that are endothermic. What are some things that are disfavorable, things that discourage processes from happening? Well, if our entropy is negative. So, for example, we are looking at processes where we have the entropy change of the system or the entropy change of the surroundings going down, or we have endothermic kinds of processes where delta H is going up either in the system or in the surroundings. So general good, entropy increases, enthalpy decreases. General bad, enthalpy increases, entropy decreases. So some general kinds of trends that we can look for in that. What are some things that we can do that could potentially manipulate our system and drive it toward greater spontaneity? Well, one of them is temperature. If temperature is increasing into the system, we will notice that the entropy of that system is going to increase as well. Because it can do one of two things. That system can take that increase in temperature and use it to transfer energy, which would mean a loss of heat, a negative delta H. Or it can take that energy that comes from that increase in temperature and go and do work. And work would also be a loss of energy and a generally favorable thing as well. So if heat comes into the system, chances are pretty good that the entropy of the system is going to increase in one of two ways. It's going to redistribute that energy in some kind of manner, either through the transfer of energy to another component, the use of work, or just simply the taking that energy and raising the kinetic energy of all of the components of the system, making more microstates possible. Because now the substance has more energy, which means, generally speaking, more degrees of freedom, more ways to move around, moving around at higher energy. When it comes to temperatures, we can monitor the change in entropy for a system by taking Q, the heat associated with the process, and dividing it by the temperature in Kelvin. And what we can see in this example is that the entropy distribution and dispersion of heat. Why does heat flow from hot objects to cold objects? Well, the answer there is actually relatively simple. It's a matter of entropy, and we can use this equation to kind of prove it here. So if I have a cup of coffee at 350 Kelvin and it loses a joule of heat to the surrounding air, well, inside of that coffee, we can calculate that its entropy is roughly 2.86 times 10 to the negative third joules per Kelvin. That 1 joule of energy divided by the 350 Kelvin that it was. But if we take that 1 joule of energy and move it up to 300 Kelvin to the cooler air, we see that the cooler air is going to have a higher entropy as a result. Taking that 1 joule of energy and transferring it is going to yield a net change of entropy in the positive. So the reason we see heat transfers happening from hot objects to cool objects until we reach a thermal equilibrium is because in that cool object, we are going to see such an increase in entropy from the heat being transferred into it that the process is spontaneous. We're going to see a greater increase in entropy in the cool object than we're going to see a loss of entropy in the warm object. And since spontaneous processes happen when net entropy increases, the transference of that energy from hot to cold yields a net entropy increase for the overall universe that we're describing here, system and surroundings. So if we think about the cup of coffee as our system, yes, our system has lost entropy because it has lost heat, but the surroundings has gained more entropy by distributing that energy in more different ways. So even though the entropy of the system went down, the entropy of the surroundings went up by a greater level, and the entropy of the entire thing, the universe, went up as well. Couple of definitions that we want to throw out here. Reversible processes versus irreversible processes. So in a reversible process, we were talking about something where we have a system that does not leave equilibrium. And so even if we are describing a process where we are pushing down on a piston, um, it's almost imperceptible to see, but this piston here is slightly lower than the one right next to it. And so even in a process where we're describing this piston going down, if we think about this approximation where we just take it from a series of 1,000 snapshots, that piston just slightly going down along the way, we can estimate kind of the change in that process. If a process is irreversible, it's done in one snapshot. The difference here is in this process here, with it being reversible, it can go the other way. The pressure of the gas that is now trapped in that smaller amount of space can push the piston back up. That's not happening in this process on the right. So reversible processes, we need to think about equilibrium. We need to think about where the reaction can go back and forth, back and forth. Phase changes are a great example of this. I can turn that liquid water into gas. I can turn the gas back into liquid. All I have to do is reverse the process. So if I add energy to water, I can get it to vaporize. If I remove that energy from the water, I can get it to recondense. All I had to do was reverse engineer the steps. Some processes aren't able to do that. I can't, for example, I can't simply take water and turn it into hydrogen and oxygen again just by removing the heat from it. Add a little bit of heat activation energy. I turn that hydrogen and oxygen into water vapor, in a rather explosive reaction. I can't reverse that process and get back to where I was. A lot of chemical processes are irreversible. Once they happen, you can't undo them without any kind of significant means. So comparing, looking at this graph here, if we compare these two graphs, so here I've got the same system at 10 Kelvin versus room temperature. And what I'll see is that at 10 Kelvin, because my relative velocity is lower, the amount of energy is not nearly as high. So I don't have as many microstates associated with it because I don't have nearly as much energy to distribute. And so while the molecules in here are capable of rotating and translating and vibrating, they're doing so to a much lesser extent because there isn't a whole lot of energy present for them to distribute that energy. Whereas at room temperature, 298 Kelvin, we see that the distribution of the low energy stretches here is considerably lower, and we have more high energy stretches available, where we're seeing higher degrees of rotational freedom, higher degrees of vibrational degrees of freedom, longer, larger, more varied translational modes. More degrees of freedom means more entropy. So at the higher temperatures, we have more microstates, more degrees of freedom, more entropy as a result. We can also see similar kinds of arguments, not just associated with temperature, but with other kinds of measurable parameters as well. So for example, in a gas, if I take a confined gas and expand its volume, expand its container, I'm going to get more microstates as a result. Because now that I have a greater volume, I have more translational degrees of freedom to work with. So when we go from small volume for gases to large volume for gases, we're automatically going to get less confining, which means more translational degrees of freedom, more entropy. We see the same kinds of effects with pressure as well. And largely the same argument. Since pressure and volume are inversely related, higher pressure systems mean that we have compressed the gas. Gas compression generally means lower entropy. Why lower entropy? Well, I've got less room. Less room means less translational motion. I have less variability in the ways that I can go without bumping into other things. With fewer translational modes, I have fewer degrees of freedom. I have lower entropy. Now, solids and liquids could do this as well, but the impacts are relatively minute. If I push on if I looking at a syringe system like this or a piston, if I do the same thing to a liquid, I'm not going to see the same net effect. Liquids aren't nearly as compressible as gases are because all the molecules are already kind of on top of each other. There isn't a whole lot of space for them to go. Solids, it's even less so. So we don't see a whole lot of change in entropy based on pressure because the volume doesn't change all that appreciably either. The other thing that we can look at is mixing. We saw this argument being made when we talked about solution making. We can also talk about it in gases as well. The mixing of gases is one that is going to raise entropy. Mixing of any two things really will raise entropy because it's going to introduce new arrangements, new ways of combining the two substances together, and that's going to lead to more combinations of microstates. So think about it again, kind of in the dice example. Only instead of two dice, we're now looking at two molecules of different kinds. Well, as you could imagine, the more blue dice and gray dice that I throw together, the more different combinations that I can get. Where now it's not just a matter of, okay, it's a red 3 and a blue 1, but now it's a red 3, a blue 1, and a blue 2. More combinations, more different ways of arranging things, more microstates. Now, just as a mathematical kind of exercise here, your book is showing that the entropy of mixing here is more or less equivalent to if I had the two gases individually expanding into a vacuum, the entropy of mixing would be the same as those two individual expansions put together. So the entropy of mixing is pretty profound. It's basically equivalent of two gases expanding into the same container. So let's talk about some ways of calculating entropy. Now, luckily for us, we went through thermochemistry in Chem 1. We saw a couple of ways that we could calculate delta H in thermochemistry. And luckily for us, some of the same ways that we calculate entropy are similar to the ways that we calculated enthalpy change. One of them is using the thermodynamic data. So if this equation with the delta S looks familiar, it's because in Chem 1, we used the same equation, only with delta H instead of delta S. So the standard entropy change for a reaction is equal to the sum of all of the entropies of the products minus the sum of all of the entropies of the reactants. Now, where do we get these values? These are the absolute entropies. This is where we would look at Appendix 4 or the tables that I gave you that we've been looking at throughout the semester here. But what we would do is, if we were looking at this example problem, for the entropy of the products, we would take 2 times the entropy of carbon dioxide in the gas phase, plus 1 times the entropy of nitrogen in the gas phase. And we would subtract from that the entropy of the reactants. So it would be 2 times the entropy of carbon monoxide and 2 times the entropy of nitrogen monoxide in the gas phase as well. So that would be what we would do. We would just need to find those values and then do our adding and subtracting to figure out the entropy of the reaction. Based, just off of pure numbers, again, qualitatively, we would look at this and say, we've got 4 gas turning into 3 gas. Chances are pretty good it's negative, but there would be, because of carbon dioxide having extra bonds, that would be, carbon dioxide should have the highest entropy of them all. We'd have to look. That's why we do the calculation. But that's the process that we would undergo. So let's take a look at an actual example here. So methanol reforming is an industrial process that has been used for generating hydrogen for fuel cells. It's done so by taking methanol and steam and combining that at appropriate conditions. The results are hydrogen and carbon dioxide. So we need to find the calculation value for delta S for the reaction for this. And to do that, we need to find the absolute entropies for each of these 4 things. And so this is where the table is going to come in. So first we want to look for methanol. So that would be under carbon. And so CH3OH. And one thing that we have to be careful of using these thermodynamic tables, phases matter. So we can see that we have 2 values of methanol here, one for the liquid, one for the gas, and they do have drastically different entropies. We're wanting gas, so that's 240 joules per mole Kelvin. Since we're in carbon already, let's just look at carbon dioxide. And so carbon dioxide in the gas phase is 214. And now we're going to flip over to hydrogen. And for hydrogen, H2, one thing that you might remember from thermochemistry is that if I have an element in its standard phase, the heat of formation was zero. Remember, the only thing that would be zero is a perfect crystal. And so we're going to find that in very few cases do we have entropies of zero. Hydrogen gas, 131. And water vapor, 189. So for delta S of the reaction, it's products minus reactants. So product was 214 joules per mole Kelvin times 1 mole plus 131 joules per mole Kelvin times 3 moles. So that's the product side. On the reactant side, it's 1 mole of methanol times 240 joules per mole Kelvin, and 1 mole of water times 189 joules per mole Kelvin. So carrying out the calculations, 214 plus 131 times 3 gives us 607 joules per Kelvin. Moles were canceled out in the previous step. And we're going to subtract that from that, the reactant side, 240 plus 189, 429. So delta S for the reaction, 607 minus 429 is 178, positive 178 joules per Kelvin. Qualitatively, we have predicted that this was positive. We had 2 gas in the reactants turning into 4 gas in the products. But sure enough, the numbers validate that as well. All right, any questions with this opening example? All right, let's end with this question then. So I'll let you go after this one here. What is the value of delta S when 60 grams of iron solidifies at the normal freezing point of 1538 degrees Celsius? I went ahead and already put in the values. So for the liquid, the absolute entropy is 34.3 joules per mole Kelvin. For the solid, it's 273 joules per mole Kelvin. All right, so this question has kind of two parts to it. The first part is exactly what we just did. So to figure out the entropy of reaction, we would take the product minus the reactant, so 27.3 joules per mole Kelvin minus 34.3 joules per mole Kelvin. And so for the reaction itself, we would get negative 7.0 joules per mole Kelvin. Unfortunately, that's not what the question is asking. That it's asking us for, okay, well, what amount of entropy is exchanged, gained, or lost when we have 60 grams of iron that's undergoing this process? And so we saw questions like this in Chem 105 around enthalpy as well. And the way that we solve them in 105 is the same way that we're going to solve them here. This value of delta S is ultimately going to serve as kind of a conversion for us. So first thing we need to do is, if this is how much is associated with 1 mole, how many moles are we actually talking about here? So 60.0 grams of iron. We need to turn the grams of iron into moles. Molar mass of iron is 55.85. So 60 divided by 55.85 gives us 1.07 moles of iron. And if we take that number of moles of iron and multiply it by our 7 joules per mole Kelvin, we're going to find that the moles cancel out. So 1.07 times negative 7, we're going to get to two significant figures, that delta S for this particular system is negative 7.5 joules per Kelvin. So all that we had to do there was just, that was that one extra little wrinkle there to take into consideration. So your homework assignment for tonight is going to focus mostly on these entropy kinds of interpretations. There's going to be some qualitative kind of things, like what we did with some of the earlier top hat questions, where you look at a chemical reaction, determine is delta S positive or negative. There's also going to be some stuff like this where we have to calculate S at a variety of different conditions. So make sure you get your last point here. While you do that, tomorrow we're going to take the next step to this. And the next step to this is, what we are going to find is that entropy becomes a little bit difficult to work with at times, because defining the entropy of the universe can be a little bit cumbersome. What we're going to try to do instead is we're going to try to frame this idea of spontaneity in terms of things that are actually a lot more manageable in terms of measurement in a laboratory setting. And that's where Gibbs free energy is going to come in for us, that delta G term. So that is all for today. So unless there are any questions, we're going to call it a day right here. And so